Okay, in this video I'm going to work through practice exam number 2 for Calculus 2. In this first example, we're told to use the general slicing method to find the volume of the following solid. Now, a description of that solid is given to us here, along with some boundaries, and they've even done a nice job of supplying an image or a picture for us. So here we've got this three-dimensional graph with the x and y axis. Z-axis, of course, would be the vertical one here. And we're told that we're kind of bounding this curve on the xy plane by x values that exist between negative pi over 2 and positive pi over 2. Those arrows are technically switched, so positive is towards us and negative is down here. So between those two regions, we're going to create a cross-section of the three-dimensional shape that are perpendicular to the x-axis, so 90 degrees to the x-axis, and isosceles right triangles with a leg in the xy plane, and also the vertical leg is above the x-axis, so it's kind of perpendicular to the plane as it is. So we've got a nice picture of the triangle that's being represented here. I think we can work with that. Now, one of the things that I like to do first is I try to determine what's the area of each one of these cross sections. Now, we're dealing with just a triangle, so I might call this 1/2 base times height. But since these are isosceles right triangles, then I know that another way to write this formula would be 1/2 of base squared. Now, upon further review, the base of this triangle is really just the y coordinate associated with the point on this curve. So we could think of this as 1/2 of y squared. And better still, the y value is a direct result of this formula. So we can say that we have 1/2 times 30 square root of cosine of x squared. If you wanted to clean this up, you could. We could take 1/2 of 30 squared times cosine of x. And since 30 squared is 900, half of that is 450. We now have 450 times cosine of x that represents the area of each one of these cross sections. Now, when we go to the integral, we could have stopped back here and actually used this integral or any of these that simplify along the way. Any one of those would have been okay to place into the integral. But we need the integral in order to calculate our volume. And since we're creating these cross sections relative to the x-axis, we're going to create a new cross section at every position on the x-axis. I think an integral with respect to x is appropriate. Therefore, our boundaries also need to be x values. And fortunately for us, those were provided as such. So negative pi over 2, positive pi over 2. And again, what we need to do is sum together all of the areas. Well, area formulas were kind of derived here. So I'm just going to find the integral of 450 times cosine of x, and this should generate the volume that we're after. It's effectively creating a triangle with this area at every position from negative pi over 2 up to positive pi over 2, an infinite number of triangles for that matter, and the result will be automatically generated for us. So I set this up in my TI Nspire calculator off screen, and I executed the integral. Make sure that your calculator is in radian mode. That'll help us when we let the calculator do the antiderivative here, and the end result here ended up being 900. So I'm curious, or I'm interested in the exact value as well as your setup, and if there's an an approximate value that this thing came out to be, then we could report that, or we should report that too. And so effectively I'm looking for, pardon me, looks like my storage device unplugged there. Anyway, I'm looking for 3 components as far as a solution: the setup, so the integral, the precise answer, and then an approximate answer if one exists. Now on the exam, you'll be given the option to complete 1 or 2. There's example 1, here's example 2. In this case, the picture is not provided to us, but the shape ends up being a little bit more simple than the other, and also the equation becomes a bit more manageable as well. Now I'm cheating just a little bit and I'm using my graph drawing tool, but let's just kind of remind ourselves that we have an x, a y, and a z axis, and we have coordinates in the xy plane. So these are x and y coordinates. So a spot here, here, and here. So 0, 0, 9, 0, and 0, 9. Now when we think about this cross section on the xy plane, it ends up being just a right triangle. It may not look like it, but this is a right angle relative to the axes. And we're told that the cross sections of the three-dimensional object that are perpendicular to the base, so 90 degrees to the flat surface here, and parallel to the y-axis, so in this direction, are semicircles. So we've got to imagine that we've got a bunch of these semicircles that are stacked on top of one another in this plane here. So it's almost like a half of a cone that we're dealing with. Now here again, one of the things that I like to do first is try to figure out the area of each cross section. The area of each cross section is going to be half of pi r squared. We want half of a circle, and it would be helpful to note what the radius of each circle is. Now the radius, of course, measures from the center of the circle to the edge, and if we look at the way this thing was described, the y-coordinate at any given spot is going to give us our total diameter of these circles, and so if we took half of y, then that's going to generate the radius that we'd like here. So I might write 1/2 of pi times 1/2 of y squared, and we could clean this up just a little bit. We've got 1/2 of pi times 1/4 of y squared, so I'm imagining this term being squared, and 1/2 of a fourth, now I can distribute, ultimately ends up being 1/8 of pi times y squared. Now that's pretty good. We know that the y coordinate in any one of these positions could also be written as a function result in terms of x. I'm going to change my perspective again just a little bit, and I'm going to think of just a top-down view of the xy plane. If I have a coordinate here at 0, 9, and I have a coordinate here at 9, 0, I'm imagining the straight line that connects those two, because that straight line is what's creating the boundary to each of these semicircle cross sections that kind of exist in the z-plane here. So this equation is not too hard to figure out. This equation for this line is y equals negative x plus 9. Negative 1 slope, y-intercept of 9. And we can make that substitution here if needed. So one way to write this equation is 1/8 pi times y squared, or we can think of this as 1/8 pi times negative x plus 9 quantity squared. So depending on how we write our integral, we now have an equation in terms of y and an equation in terms of z. When it comes to our volume, we do want an integral between two boundaries. And here again, I'm trying to think about the cross sections that are used to develop the three-dimensional shape, and it looks like those cross sections, each individual cross section lives in an x coordinate or an x position. So I think developing an integral with regard to x would be appropriate here. So that tells me that my boundaries have to live with x values as well. Now we're running from 0 on the x-axis up to 9 on the x-axis, so I'll use an integral from 0 to 9. And then the area formula, well, I'd want to choose the area formula that's based on the variable x. So I'm going to use this one here, 1/8 times pi times negative x plus 9 quantity squared dx. I believe that's going to be an integral that obtains the answer that we're looking for. So I've set up my integral in the TI calculator now. This appears to match what I've written on paper, and I'm satisfied with what I had there. So when I press enter, I now have a precise result, and if I press Control Enter, I've got an approximate result to report as well. So we can say that this is 243 pi divided by 8, which is approximately equal to 95.4259. 75.4259, and that would be a good set of answers to report on the test. I'm going to stop this video here just to make a series of shorter videos rather than one really long one. And either of those techniques would be perfect for an approach to problem 1 or 2. In problem number 1, we had a bit of a more complicated equation representing our area. But in problem number 2, we actually had to establish the picture and the equation ourselves. So I'll let you decide which method you'd like to illustrate on your exam. Thanks for watching.